Welcome to Embedded. I am Alicia White, alongside Christopher White. Our guest this week is Cindy Harnett, professor of electrical and computer engineering at the University of Louisville. We are going to talk about new sensors, soft robotics, and, well, probably our alma mater.
Hi, Cindy. Welcome to the show.
Thanks. It's good to be here.
Could you tell us about yourself as if we met at our, oh my God, I don't want to count that high, reunion?
Okay. Since graduating, I went to grad school and I drifted from physics to electrical engineering and going to applied physics and then working at National Lab and then going into academia. So I've been a professor in the electrical and computer engineering department at U of L for almost 20 years now.
Wow, congratulations. We're going to do lightning round where we ask you short questions and we kind of want short answers. And if we're behaving ourselves, we won't ask why and how. And are you sure about that? Are you ready?
Almost.
It doesn't help you to pull up the questions that were in your sheet. Those were only examples.
Okay. Well, I do have a long acronym on there and I'm not sure if I can remember what it is. So.
Okay. We'll be sure to do that one.
Oh, no.
What mud dorm or dorms did you live in?
North dorm.
That negates the next question of unicycles or fires.
Well, she can still answer.
Okay, unicycles or fires?
Fires.
Favorite sensor?
The time of flight sensors or LiDAR.
Favorite soft robot, fictional or not?
Baymax.
Oh, yeah. Okay, that was kind of a softball, wasn't it?
How are you supposed to pluralize MEMS?
It's hard, and if you're writing a paper and everybody says MEMS for microelectromechanical systems, and you're just talking about one system, no one calls it a MEM. Like we made a MEM. So you kind of have to work it in there in the field of microelectromechanical systems or MEMS, blah, blah, blah.
Not MEMSes.
No, and we just avoid the... That's right.
It's always MEMS sensors.
That's right.
Yeah, right next to your ATM number or your PIN number.
What was your concentration?
At Harvey Mudd, I was physics, but I tried to be an art minor.
Yes, the concentrations were a lot of trying to be something. I remember that.
I got an art one.
I know.
I did art and education.
Awesome.
No overachiever in that section. Okay, let's see.
Favorite acronym?
Yeah, that's the one.
Oh, yes. I had a project where we had environmental sensors, so we cooked up this name Salamander for it. It's serial amphibious linear arrays of micro and nano devices for environmental research.
That's one of the longest ones I've ever seen.
And it worked out. She didn't have to get rid of the E or anything.
How long did that take to devise?
Maybe about a week. I had 2 summer students and we were working it out.
Complete one project or start a dozen?
One project.
Do you have a tip everyone should know?
This one I heard from someone in our hackerspace. If you need to put things in Ziplocs, write the label on the Ziploc before you put the things in. It gets all lumpy and you can't write on it anymore after that.
That's a good one.
That makes sense.
It's just basic.
I mean,
it works.
It sounds so obvious, and yet I certainly have done it the other way. Okay, so you sent me a few papers from your lab, and I have lots of questions, but Chris hasn't read the papers, so we're going to have to talk a little bit about what they were.
I assume that the listeners haven't read the papers either.
Oh, no.
We have listeners, remember? Yeah,
but we don't care about them. Sorry, listeners. We do care about you a lot, but they'll have links to the papers.
Okay, well, that's fine. It's not just for my benefit.
Right. Okay. Let's start with the actuator one, if you don't mind.
Okay, the Sesame one.
Yeah.
Not our longest acronym. This one, we've long been working on using strain to go from something planar to something that's kind of folded up. And usually I've been doing that at the micro scale using silicon wafers and heating them up. But you can also do something like a slap bracelet. If you can imagine one of those there's two layers in a slap bracelet. One of them is curved one way and one's curved the other way. And when you put them together, neither layer is really happy. So you've got the two states of the thing. It can be flat or it can be rolled up. And that's the integrated stress concept. Another way you can do that is by stretching a piece of spandex, for example, something elastic, and then applying things. People are doing 3D printing, for example, on stretch fabrics. When you let it go, it pops up, it goes 3D. So the Sesame project was that concept, but with wire inserted into the stretch spandex.
Not just any wire.
Yeah, that's right. Not just any wire. We have some shape memory alloy. By now you can get this stuff commercially fairly easily. It was developed in the 60s, I believe, a combo of nickel and tin, so it's called nitinol.
Nitinol. I worked with nitinol in a previous job, yep.
Yep, now you can order it by the foot or by the meter. And so we have a nice machine that we can use to insert that using overstitching. It's kind of a fancy sewing machine. So we were able to put the nitinol wire in the stretched material and let off the stretch by releasing it from the hoop we had everything stretched out in. And we got this kind of egg crate structure. But when you heat the nitinol, it stiffens and it flattens everything back out again. So you got this soft sheet that you can crumple up, but then you could heat it and it would flatten out again.
So looking at the video, which was also entertainingly musical, it looked like it was embroidery hoops, and then the stretched fabric, and then an embroidery machine sewed down the wire. And then once you let it out of the embroidery hoop, it would go to its, I want to say deformed position, its 3D position. And then when you, I guess, put some current on the wire, I didn't see that part, it would go mostly flat. Is that, did I get all that right?
Yeah, that's right. And so something that starts out as a circular pattern, we have a machine that can spool out wire and then do a zigzag stitch over it so it doesn't stab the wire most of the time. And so it really firmly attaches it down, but everything's stretched out in this hoop. It's all flat. And the great thing about nitinol is if you want to heat it, well, it's a wire, so you can just run an electric current through it. So if you have an embedded system, you could put current through a transistor. It takes maybe half an amp. So kind of quite a lot of power, but it'll flatten everything out.
The thing that really struck me with this paper was the circle. You have okay, let's go back to the visualization of the embroidery hoop. You use the embroidery machine to make a circle of the nitinol, and then when you let it go, it goes to a saddle shape, a Pringles shape.
A Pringle, yep.
And then you heat it up and it goes flat again. So I see this shape a lot with curved origami, which is something that I've talked about on the show, and it's just something that I do a lot of. And it seemed like the reason for it was similar to the reason for origami, is that's how you get a less strained shape given a circle.
Yes, you have this trade-off between the boundary, like the wire wants to be flat, takes some energy to bend a wire, and the surface area of the circle. So this fabric is stretched, it's kind of unhappy, it wants to be smaller. And when you have a surface that has an edge and not quite enough material in the area of it to fill in that edge, it has to go saddle shaped. It's got negative curvature. And the opposite of that is if you have too much material, more than pi r squared, then that material likes to go dome-shaped, mountain or valley. And if it's a perfect amount of material, it's going to be flat, but either too much or too little, and something's got to go out of plane.
And then you also have this thing where you can put the nitinol in a figure 8 pattern. I mean, it's not figure 8. It's like a figure 36. It's a bunch of circles put together. And then it crumples up. And I think you said egg carton, and that's about what I would say too. How did you come up with that pattern?
That one, there's a natural array that forms when just putting circles next to each other. And so we wanted to have a lot of separate Pringles, if you want to call them that, or actuator cells run using one current. Otherwise, we'd have to have a multiplexer and a lot of circuitry in the fabric. So we said, let's just have a whole bunch of them in an array and fire them up all at once. So having this S-shaped kind of serpentine pattern with one wire going through, there's actually a lot of wrong ways to draw that so that it doesn't form the loop that you want. And there's probably an algorithm for it. We did a little trial and error. So we think we've got a 6x6 array of circles that's all drawn by one path. But it took some graph paper to do.
That was another area where when I saw what it looked like in its crumpled state, I was like, oh, I know that origami pattern. And so it was super weird to realize that the pattern you used to get to it is only somewhat different than the pattern I would have used to get to it in paper.
So do you have an algorithm for that to save me the graph paper?
I have whole Python scripts.
Yay!
More importantly, there's the origami simulator that will show the results. That I bet will show some of the nitinol results. And I just want to go off and try this because what if these do overlap? It would be so exciting.
Mm-hmm.
You're going to put nitinol in your origami?
I don't need to. The folds act as the nitinol.
Well, but you can't put a current through the folds.
Yeah, if I put the nitinol in the origami, I could flatten it and have this little weird walking robot.
Yeah.
Which is actually why you're doing this. It's not just that it's cool.
That's right.
You can stop. I mean, it's just, yeah.
I mean, the Pringle shape is one that I've seen before with soft robotics because it's very similar to a claw shape. You just close that Pringle all the way down, and suddenly now you have fingers, and they're soft fingers. They won't hurt people, but they can grip things. How big have you gotten? I'm going to go with the Pringle shape. How big have you gotten the Pringle?
About actual Pringle size. So we learned from developing this project that there's a certain realm. If you make your Pringle too big, then the fabric in the middle just kind of wrinkles up, and it gets to its happy area. It's all trying to shrink, and it gets to this place where it's happy before it's really formed the Pringle shape. If your Pringle is too small, it doesn't settle shape at all. It just stays flat, and it says, I'm going to not bend, and the fabric, you're just going to have to stay stretched out. It's always this competition between bending of the wire around the edge and stretching of the fabric. So there's this sweet spot in the middle. It turns out to be, for the diameter of the wire we used and the hardness of that wire, about 5 centimeters. So it really did look maybe a little bit smaller than a real potato chip. But if we wanted to go bigger, we could do that. You can get larger diameter wire, and that's what we would have to do.
It would be fun to experiment with the diameter of wire and see what the maximums are for the different diameters. Didn't you have a position open in your grad student lab, and when can I start?
Oh, there's a fellowship, so and it's this month that we want people to apply.
I'm sorry. Easily distracted by what sounds like awesome toys.
Come and visit.
So have you found a practical use for these yet?
We've taken them and applied them since they do take a lot of power and a lot of temperature changes going on in this material. We've applied them to bistable elements, so little pieces of plastic, for example, that are attached at the ends and they kind of pop up or down. And that's where we see these being most useful in a soft robot that can move a little bit at a time, store up a little bit of power, and then pop one of its actuators to another state. We have a really old paper that says you can make any shape this way, at least with the 1D array of these bistable elements. So we were always looking for muscles to put on the things that were compatible. A big driving goal behind my work is to start everything out planar. That's really great for fabrication, simplicity, and speed. If anyone is an art major and they took a painting class versus a sculpture class, the paintings get done a lot faster than the 3D stuff. And planar stuff is also something you can align. So if you have different layers, you can stack them and then fold. It's a lot harder to do that after something's gone 3D. And that mindset probably comes from microfabrication, where everything's on the silicon wafer. It's really it's got a really great dimensional tolerance, really easy to line up. There's whole machines made for aligning things. So my mind might be poisoned by that.
Actually, I mean, one of the papers was also had MEMS. When you talk about doing things like that, the thing you just said about wafers, do you always mean MEMS stuff, or are there different technologies we're talking about when we look at small systems?
For me, it's MEMS, but there are really interesting 3D printing methods like the 2-photon printing that are starting to get down to the microscale too. I haven't done that.
Can you describe that? I don't think
I've never heard of it.
Heard that one.
Oh, let's see. There's a system that you can get that has lasers in it that when they both cross, it's kind of like a resin printer, but it's using these highly focused lasers. And I forget the resolution that it can get, but its build envelope is 3 millimeters high. So that's it. It's big. I mean, it's like maybe 10 centimeters across, but within that 3 millimeters, you're getting full access to the resin with this 2-photon intersection.
Okay.
Huh. You could make some really small things.
Yeah.
Bio machines.
Mm-hmm. Yeah, things that would be hard to make using conventional MEMS.
But then that's actually a little bit more 3D than conventional MEMS.
Yeah, it has all the pluses and minuses. So MEMS, you might be thinking I'm limited to layers, right? Depositing a layer or etching a layer. And it's hard to do overhangs or anything. You can do it, but with this 2-photon printing, you can get really intricate geometry. Like you can do a little Capitol building with the little pillars. I think that's one of their test structures. But it's all made out of the resin.
Okay. It's like, actually, let's start over with MEMS, because not everybody is like, what is MEMS? So I was introduced to MEMS with accelerometers and gyroscopes when they became sensors that were chips instead of physical objects. Do you know how a MEMS accelerometer works?
Usually there's a little mass and there's a thinly etched beam. The mass is really tiny, but it's on this very thin beam, so it's able to move in response to forces. And if you can measure that motion, then there's a bunch of different ways that people do the measurements. So they can measure they can put a little strain gauge, like a little resistor on the beam, or they can use a capacitive method to sense where the weight is, or the mass, I should say. So that part is almost, the mechanics are done as the electrical engineering side.
Mm-hmm.
Cool. That concurs with my diving board analogy in my head. How the gyro works, I have no idea.
Same thing, but just a little spinny thing. I don't know.
Yeah. Somebody will chime in and say there's other ways besides the mass on a stick. Like there's little hot air sensors and temperature-based accelerometers.
When I started with MEMS before the year 2000.
The year 2000.
The distant future.
Exactly, the distant future. They were new and shiny, but now like they're everywhere and they have all kinds of sensors. Do you have an idea for what you find is the neatest sensor that's out or coming out?
Oh, right now I'm really liking these magnetic field sensors. So kind of basic. And you might think there's no moving parts or need for MEMS, but anything that's a vector sensor, like suppose you want to sense the magnetic field in X, Y, and Z, then you have to have some sensor element that's oriented along each axis or some way of distinguishing different components. And so the MEMS process might come in there because it would fold up these planar fabricated materials into things that respond only along a certain axis. But I really like them because they're so small and they're useful for a project that I'm working on right now.
Is it the bird vision sensor project?
This one, bird vision sensor.
Well, because birds not only they not only can tell which way is north, like what we use our magnetic sensors for usually. They can see how probably they can see how it enters the earth. And so it's like, I want to say another color over their vision and they can just.
Oh, yeah.
Anyway.
I think I saw that picture. Yeah, I think I saw that somebody simulated what the bird sees magnetically.
Bird physics.
And usually we're trying to do background subtraction because there is this Earth's magnetic field and it's kind of getting in the way. And we love the prospect of being able to turn on a nearby current in a wire and then use this little sensor. I mean, these things are less than a millimeter square, even packaged up. Use it to sense some wire that's moving rather than sense what the orientation of the whole part is.
I'd like to thank our show sponsor this week, Nordic Semiconductor. Nordic has a vast ecosystem of development tools. It helps us reduce our development cycles and accelerate the time to market. For example, the NRF Connect for VS Code extension provides the most advanced and user-friendly IoT embedded development experience in the industry. Nordic's Developer Academy online learning platform equips developers with the know-how to build IoT products with the Nordic solutions. Nordic's DevZone brings together tech support and a community of customers to provide troubleshooting and assistance on technical topics. Visit these key websites to learn more: nordicsemi.com, academy.nordicsemi.com, and devzone.nordicsemi.com. And to thank you for listening, Nordic Semiconductor has a contest to give away some parts. Fill out the entrance form and you're in the running. That link is in the newsletter and in the show notes. Going back to your projects and your papers, you had one that was for bend localization, which I thought was really interesting because I've had client projects that wanted to look at how limbs bend for physical therapy. Mm-hmm. But I think yours is quite a bit different. So what is OptiGap?
All right. This was a recent graduate, Paul Bupe. He looked at some sensors that we'd been working on. And so we had developed a stretchable optical fiber, and he wanted to apply this to a shape memory wire robot that he was working on, because you really, in these shape memory robot devices, you want to know when it's done the job it's got to do. And then you can turn off the 0.5 amp or whatever, because that's costly, right? But he needed a soft sensor that wouldn't interfere with the way it wouldn't push the actuator around. So he took some filament that we'd been using just as a length sensor and cut a little gap into it. And literally right there at the gap, he just cut it with a razor. If you bend it there, the light sprays out.
Right.
It looks like water coming out of a hose in the ray tracing simulation he did. And if you got a detector at the end of the fiber and you bend it, you're going to say, hey, where's my light? It must be bending at that one spot. So fairly straightforward concept. But of course, he wanted to measure bending at different locations, not just one spot on his actuator. So he put a bunch of gaps and he put several fibers side by side and a really great programmer. So he got a machine learning setup going to identify which of these gaps was bending. And from that, backtrack and figure out the shape of this limb that he was working on.
So, okay, just to paraphrase again, a bundle of optic fibers, and some of them are cut a little bit at different places so that when they bend at the bottom, the ones with the cuts at the bottom lose light more than the ones that aren't cut there.
Right. Yeah. If you have two fibers in parallel and one has a gap at the place where you have a hinge and one doesn't, you're going to see a really dramatic difference in, fiber A that doesn't have that gap and fiber B that does. And so even though every fiber is stuck on the same object, we can use that to get some spatial information out. Is it A or B? And he would scan the lighting and have it all piped into one photosensor.
Okay. And then the machine learning. So what is the difference at the sensor between those different positions then? Is it a difference in intensity because they're further away and there's more loss, or?
It's intensity.
Okay.
So if you had and you know which fiber you were lighting when you were measuring. So
okay.
Yeah, if you were lighting fiber A and you got a lot of intensity, but fiber B had hardly any intensity, then the hinge where B has the gap went. And so he did that with 3 fibers and with multiple cuts. And he would get like 2 to the n-1 sensing locations for n fibers.
It sounded like a key scanning matrix.
Yeah, okay.
Yeah.
And the data he got out of it while he used machine learning on it, it seemed like you could just use a simple filter.
Yeah, I think he'd like to push the limits of his programming skills and speed up how quickly it would recognize small changes and throw out some of the noise. But it is fairly digital. Is that one ready to be used? Yeah, we have a research disclosure on it, and it's up on the U of L site. So he's interested in commercializing that.
How important are patents to this type of work?
It depends on if you're trying to develop fundamental new concepts or trying to commercialize. Mm-hmm. So definitely if you're trying to commercialize, our tech transfer office, like most colleges and universities in the U.S., really encourages IP. But if we publish it and don't patent it, that is still good for the academic side, right?
Yeah.
Yes.
And it may let more people make use of what you did. So there's kind of 2 sides to it.
Do you encourage your students to publish before looking into patents?
Yes, and usually that's the first thing. I want to get everybody through with a paper when they have a project and have that paper in mind. So that's number 1 for me.
Both of these, the actuator with the nitinol. Somebody should have given me a Post-it note with that written on it. And this OptiGap, they're things that sound like I could do them. Mm-hmm. I mean, if I had the parts, they seem like they are recreatable without a huge lab. Is that intentional?
I think so. It's something that is driven a little bit by the way students come to my lab. I have a lot of summer students, and if they have to learn MEMS, they can do it. And in fact, we have a great REU program where they do learn the microfabrication skills, but they only have about 10 weeks, and they get the things done in the last couple of weeks, and then they're gone. But if I can get them doing something on day one with stuff on the bench top, they tend to get more done.
REU is research experience for undergrads?
Yes, that's right. Research experience for undergrads.
And so the goal is to get them to be thinking about sensors and doing sensors even as they're learning about the MEMS processes and how to build those.
Yeah, there's a lot of analogies between the MEMS process that we do. We get things to pop up from the surface and kind of roll up, and some of these larger scale things. And it turns out a lot of these larger scale things like the slap bracelets and the bistable structures still work at the micro scale, but you can't put your hands on them and feel where they have a sweet spot like you can if it's a beam that's you can put in your hand and flip back and forth. And it turns out there's an ideal spot to put an actuator on some of these bistable little plastic beams. If you took a piece of plastic and kind of push the ends together, it would make a bow shape. And you can imagine snapping that up and down. Snapping that up and down takes a little bit of energy. And there's one spot in particular, about halfway up it, that it's really easy to cause that thing to flip. I'm going off on a little bit of a tangent, but you don't really get the insights into that from the micro scale structures alone.
Yes. I mean, bistable structures should be obvious. It's in the name. It's either in state A or state B. But when you hold something and can feel it go, feel that springiness that happens as it launches from one state to the other, it's very helpful.
Mm-hmm.
Thinking of those little toys, the little plastic rings that have a dome, and you push the dome in, and you set it down, and then 5 seconds later, the dome pops out and it flies up.
Yeah. It turns out those are harder to push from the right on the center than a little bit down on the side.
Huh.
You can kind of roll them through. So if you're trying to make a micro scale one, you might think I better put my actuator right in the middle, but it's not actually the best spot.
Wonder why that is. Huh.
I bet she could tell you.
That was an invitation to elaborate.
There's an inflection point that's very important. Rolling those things through.
One of the things in the papers was the math. I mean, when I read papers, I do expect to see some math, and usually I skip those parts. Let's just be serious. At least until I understand what it is I need. But I was actually a little surprised to see the modeling in the OptiGap and Sesame papers, because it seemed like the work came out of the modeling instead of the fabrication. Is that correct, or did the fabrication come first?
We did it right. I mean, we fooled you. The fabrication has come first, but we aim to fabricate something that we can model and try to keep it, the element that we're using, simple. So we haven't done a model of like the 6x6 Pringle array, but we made a model that would be of one cell. And because of my background and the people that I work with, we don't have the finite element modeling focus that maybe a mechanical engineering group would do. This is the one where you could picture a model of a truck and something like a really complex object, and you're looking at the airflow going over it, and you have to draw up that truck in your modeling program and simulate each little piece of it. We're more like, let's model a circle and write some equations. We might do ray tracing on an optical fiber, but that's as finite element as it gets.
Okay. That's actually kind of reassuring, because I wanted to play with the items, and I didn't want to have to understand the math in order to just play with them. And it sounds like I could just play with them.
Mm-hmm.
But I have been doing a lot of simulation lately, and I have to admit, simulation and physics, they don't match as well as I was promised they would.
Who promised you?
Well, that's the thing. I sort of promised myself that one.
I could have told you that.
How much do you need to model things in order to believe them? Or do you use the fact that you can fabricate it as a way to shortcut the difficulties of reality?
I think it's a massive shortcut. So we have a lot of materials on the desks and a lot of tape, and we're putting things together and going, we could make something, but is it going to be strong enough to do a job? So some of we've got to play around with it in the beginning just to see if it's worth doing. If we model it, we're usually motivated by getting some kind of design rule out of it to get rid of some of the prototyping that has to be done in the future. So one example is this Sesame project. We found a relationship between the Pringle diameter and the wire diameter that if you keep it constant, and I think there were a couple powers in there, like a cube and a fourth. If you keep this term constant, then your Pringle will scale up or down. It's going to look kind of the same. And that's really why we want to do most of our modeling. Get some rules out that somebody could use to adapt what we did to the problem they're trying to solve.
Cool. Okay, we had 2 more papers and we have a bunch more questions. So let's see. The bio-inspired robotic finger driven and shape sensed by soft optical tendons. Now, I have to admit, the picture on this one looked a lot like that time I poked holes in a straw and had a string that threaded through it, and then I could make little fingers with strings. Have you done the finger straw string thing?
I think I had some puppets that had little strings in them. Yeah, that's the basic principle. And this was our group. We were lucky we got a mechanical engineering grad student, Michael Hunt. She was the first mechanical engineer in our group. And it's a really common crossover for electrical and mechanical engineers who work on MEMS or robotics. Those two fields, especially, sometimes you can't tell who's who after a while. So it works on principle like a straw with a string or a tendon in it. But she also got the optical source and detector plugged into the ends of that tendon. So this thick, kind of stretchable tendon is doing a couple of different jobs, moving the finger and then also sensing how far the finger has moved using the light signal.
Couldn't I use the string length movement for that? Like how many times I had wound it?
There's a lot of tendon systems that do that. And a common question that Michael was addressing. So the big difference here is the stretchability of this optical tendon. It's made out of TPU printer filament, so another material that a lot of people have access to, but it's a little bit stretchy. So the length of the tendon depends not only on the shape of the finger, but the force you're applying, and also is the finger touching anything?
Yes.
Because you can apply a lot of force, and then your spool will be moving, and your fiber would be stretching, and you'd have different amounts of displacement depending on if you were pushing against something. The motivation for using something stretchy was it resembles more closely the human tendons or biological tendons, which are a little bit elastic.
Sometimes too elastic. But okay, so that makes a lot of sense. And then being able to add the sensing would be necessary if your tendons or strings were elastic, because you wouldn't really know whether it was blocked.
Is that the same sort of sensing that you mentioned before with the cuts through a bundle, or is this something different?
This is just amplitude, and the light attenuation is coming from the deformation of this fiber. It's going through these joints, and it's going over a few places that make it go a little bit squashed.
Okay.
So a little bit pinched. Yep.
And then it loses internal reflection or something. And Okay.
So embedded optical waveguide sensors for dynamic behavior monitoring in twisted beam structures. That is not at all an acronym. That will never be an acronym.
We didn't have time to acronymize that one. It'd take a couple months.
This one also used the OptiGap.
Yeah, this one, we changed our, so we've been using materials that were just repurposed, like printer filament, especially. That's been a really great stretchable optical fiber. But in this one, we wanted to sense twisting around the fiber's own axis. And the reason for that, I can go back a step and say we had a twisted beam that, if you can imagine a ribbon, it's kind of a rectangular shape, and then twist the end of that ribbon 90 degrees. Mm-hmm. And it's got a really interesting property. This is based on a collaboration with researchers from Oregon State, San Diego, and Arizona State. You shake this twisted beam and it starts to circulate at the end. And that circulation is really good for robotic walking. If a leg kind of goes in a circle, it can hit the ground and then it can go up and it can move over a little bit and hit the ground again in a different spot. So long story short, we wanted to be able to twist these beams, left-handed or right-handed, to get different direction gates out of the same actuator. Well, why do we need a sensor for that? We need to know if we've achieved the twisting we want, because once again, we're trying to use a shape memory wire. This time it's twisted up inside the core of this twisted beam, and that takes a lot of power. It's also starting to heat everything up in the surroundings, getting to about 100 C. So we want to know when we're done. And so we need a little soft sensor that wouldn't interfere with anything. So our summer student made a square cross-section fiber out of really clear type of silicone, kind of like a gummy worm. And she found out when you twist this square cross-section fiber up enough, it starts to lose light. And that was enough to tell whether we achieved the left or right-handed twisting.
And it lost light in a way that lets you tell the direction, the chirality?
And that is a great question. So what is the difference between a square that you've twisted right 90 degrees or left 90 degrees in terms of light transmission? Not much. So she had to pre-twist it.
Oh, and then you were either untwisting it part way or untwisting it the whole way.
That's right.
Okay. I was thinking there was going to be some polarity in here, but yeah, okay.
Yep. Huh. And so that's a challenge, because if you took a rubber band and you pre-twisted it a lot, you've got a propeller. I mean, if you ever had one of those little airplanes. So it's got to be a really soft material. So we had a really soft silicone material for that.
But now I want to spend 10 weeks trying to figure out how to improve that so you don't have to keep that tension. Okay, I'm going to go back to college.
Go back and study, maybe boiling down to chemistry at that point.
I always wish I had taken more mechanical. I just sometimes feel that that's probably what I need more than anything, more than the OChem that I actually want to take.
Mechatronics.
Exactly, mechatronics. Okay, so you've been working on interesting sensors, and what are you most excited about in the sensor space right now?
I like the idea of putting sensors all over the surface of things.
Yeah.
So they can sense the local environment. And it's just more possible now than it used to be. And these chips are getting really small. So I had mentioned that magnetic sensor chip. There's also temperature and sort of resistance sensor chips in that size range that are square millimeters, and they output a digital stream. So as long as you can wire them up, you can get local data. And then there's these fiber-based sensors that are as soft as the material they're going into. So some people call that mechanically transparent. Multiplexing and getting that spatial information out is getting easier. So one way to do that is not only looking at the intensity of the light that gets through these optical systems, but the time of flight. So putting a LiDAR sensor at the inlet and outlet, people are doing that. We did that to get some spatial data encoded on the pressure data. And then there's tiny wireless sensors going everywhere. Almost printed. You've seen those tattoo-like wearable electronics.
Yes.
It's very exciting right now.
Your answer is one that I think I would have too. It's the sensors are really cool, and there are all kinds of new sensors always coming out, although often they're tweaks on old sensors. I mean, we'll be getting more chemical sensors, but they're all going to be about the same. I would love to know more about brand new sensors. But I think that the truly interesting part is the arrays, is being able to throw a whole bunch of sensors at a problem. And it's kind of like the LED arrays that we had LEDs for a long time, and then we started getting things that let us have lots of LEDs. And now, I mean, you can have thousands of LEDs if you can figure out how to power them.
Right.
And we're going to end up doing the same thing with sensors, that you can have nets of sensors. It will just be really cool. I mean, I think we'll have clothes of sensors. And I like mechanically transparent. That's an interesting concept, one that I had not considered. Okay, so let's go to listener questions. We had one from Ellie. Ellie, thank you for introducing us. Her question was, how has research scale MEMS fabrication changed for folks at smaller universities over the past decade or so?
Okay, over the past decade, there's a process called MUMPS that's been around a while. It's much older than the past decade, but MEMS is so diverse. So MUMPS is like, if you want your device made, use these layers and these processes in this order, and you can draw your geometry and have a part of this process that goes through. But the variety of materials that people are using in MEMS, I think it's greater than, say, if you're making a lot of transistors, you want to use some specific materials, and you can usually achieve your architecture using the given process. But in MEMS, we're trying to introduce some strain and get these things to go 3D. It already doesn't belong in the MUMPS process. So it's good, but it doesn't have a really perfect analogy to like VLSI and chip fab because of the material diversity. So you start needing to do your own. And one thing I wanted to add in there is that when doing your own process, there's usually a disadvantage to going big with your wafer. So using an 8-inch wafer, which is small by industry standards, is a huge expense. So universities kind of stuck to the 4-inch wafers. And now the technology that handles those is getting ancient. I mean, it was ancient probably 10 years ago. So using really old computers. And I feel like people maybe in this audience, if you can repair and keep old computers going or hook a valuable old machinery into a new computer and keep it going, there's always going to be a need for that, at least in these university clean rooms.
It's funny. I was thinking things like tiny tape out, where people are making their own chips. And I was like, okay, well, that's MEMS has got to be similar to that. And people can try their own sensors, but you're telling me that MEMS is different.
If you want to have a magnetic sensor, for example, you might have a magnetoresistive material, and maybe no one else on the MUMPS wafer wants that material. So do you get your own step and everyone else has to cover up their part of the wafer during it? I think there's a lot more different experimental materials people are trying to use.
It's sad that we can't have more experiments there. And the reason it sounds like is because once you say clean room, everything gets 100 times more expensive.
And it takes longer than you plan.
Right, because when I order a chip, I just order a chip and it comes to me from DigiKey or Mouser or wherever. But when you design a MEMS sensor or any sort of fabbed chip, there are multiple weeks as you lay down each layer, right?
Right, especially if the old computer has blown up and you need a new computer.
Are you having computer trouble this weekend?
See, which machine is it now?
And none of them are as powerful as a Raspberry Pi, right?
Right.
You could just replace them if only you could just replace them.
Mm-hmm. You don't have the ISA card that you need.
Do you have Windows 95 on all of the systems?
I can't mention that.
Do you think we are headed towards being able to have smaller scale MEMS inventions, devices, fabricators?
Well, I think one thing that's coming up is direct write. So most of our processing is done using photomasks, and that's like a stencil that covers the entire wafer. But the direct write using a laser to write patterns has gotten faster. So it's kind of like writing with a mechanical pencil. It's very slow, right? A fine line, but it's really sped up. So at least on the design and iteration and cycling side, direct write is making that go faster. You can imagine making a photo mask. It's really going to be a piece of glass that if you don't like how that design worked out, it just goes on the shelf and you start over. And you have to cover that whole area with designs where you might be able to iterate faster if you can change the design in, I want to say edit, but in your CAD program, and then write it directly to the photoresist that afternoon or 5 minutes later. So I see a bright spot there. We also have machines that can lay down metal we have an aerosol printer, and that can make lines sub 100 micron of silver or whatever other ink you can formulate that works with it. And then there's inkjet printing. So printables are going to take care of some of this materials integration problem. And then you mentioned LED arrays. So that's really driving a lot of assembly innovation. Can we take an array or take an LED? Can we take an LED off a wafer that's usually it's a gallium arsenide wafer or some non-silicon, it's always non-silicon, and pluck it from there and then put it onto the background for this big TV. And that demands high speed, and it's sometimes called hetero integration, picking a tiny piece of wafer that's been cut out, laser diced from this other material, and then aligning it fast enough to make a big TV that you see at Sam's Club or Costco if you're in the US. And industry is pushing that along. So those three things, direct write, printing, and then this third category that's kind of pick and place, but sometimes called chip printing, really going to speed things up.
Every time I think the industry is getting boring, I hear about things that are going to make it interesting.
People always want to do more.
More and cheaper and better and different. And yes. Let's see. Do you have any papers coming out that you can talk about?
Oh, we have one that's about letting these slap bracelet-like microstructures off the surface. We used to do that by, we would lay everything down, and you can imagine a bunch of slap bracelets, but these things are about 1 millimeter long. Lying on a surface, they're taped down with a piece of Scotch tape. And we used to release those and let them go curly by putting them in a etch chamber but it's really hard to see what was going on in there. It's kind of hazy. And we got frustrated with that. So we took them out of the chamber and we made a way to release them in front of a high-speed camera. And that's been pretty exciting. You can see all these things curl up. It takes them about a millisecond to go from planar to 3D. And that paper is just coming out.
This goes back to bistable and being able to see where the best place to actuate to move between the stable states or not.
This one, it's bistable, but it's not really reversible. So it's I don't know if it's really bistable or not. It's like this thing really wants to curl up, but we've glued it down. And you can let the glue go once. When you let it go, it kind of jumps up. You can flatten it out again. So it's reversible in the sense that you could heat this thing up. It's got a metal top layer and then an oxide, really kind of a thin glass back layer. And when you heat up the top layer, it's metal, it's going to expand and everything's going to flatten out. That's not really, I guess it's cheating a little bit to call that bistable. You have to change the temperature of the whole environment to get it to go to this, cool it down and it curls up more, heat it up, it flattens out more. It's not really mechanically bistable.
Bistable more implies that the energy between them is not huge. It's just getting over a little hump.
And it's got a little barrier. Yep.
You've given me so much to think about, and now I want to go off and dream about different sensors and what I can do with them.
Go buy a spool of nitinol.
Yeah, I do.
I do wish there was another way of making those wire-like memory things work apart from driving what's relatively high current for our kinds of electronics through it. Is there any work on... nitinol's been around forever, like you said, and I remember working with it at a medical company, although I don't know that we put a current through it. It was for the cardiovascular stuff. That was the main thing that gave shape to the catheters for artery stuff. And I don't remember how they actuated that. It wasn't with current, though. I think it was just like it was in a shape that was preferred, and if you twisted it or something or gave it a force. But anyway, question was... Is there anything else coming along in material? Have people continued to work on materials like that? Or is that just like, nitinol is the only thing we know how to do?
There's upsides to nitinol that it's really easy to interface. It doesn't solder well, but other than that, if you can plug it into a circuit, you don't have to do anything else. Like there are other shape memory materials, but they might be polymers. Mm-hmm. So you have to wrap that with some kind of heater wire. And with nitinol, you just don't have to do that. But people are tired of thermal actuators because they're just power hogs.
Yeah.
And so many materials do shape memory or shape change using temperature. They do really cool pre-programmable things, but the Holy Grail is something that's capacitive or electrostatic. And so people have worked on dielectric elastomer actuators that are they're kind of capacitive. They don't draw a direct current. They need a high voltage, though. And then there's electrostatic clutches. So they're not actually the main muscle in the system, but they can grasp onto a tendon or let go, and maybe for fine control. So those are some active areas right now. And then there's other fluidic methods. So there's the Hassel actuators that use an electrolyte to inflate or deflate soft robotic muscles.
Is this like, soft robotic muscles? I was thinking e-ink, and talk about something that's bistable, requires a high current or high voltage.
High voltage, yeah.
But brief. And that's what you need. Part of the problem with the nitinol is that to keep its one state, you have to continue providing the power.
Right.
The advantage to e-ink is you provide the current and then it goes into its other state and it stays there.
Mm-hmm. What
we need is nitinol that is crossed with e-ink. Okay, go off, make That's it so.
Right. Yes, if there were something that were not high voltage and not high current, high voltage isn't that bad of a problem. You can generate it in a really small space. But a lot of those actuators, people push the limits and then they just pop.
Which, when you're making human interface robotics, is not the best thing.
No. They usually pop pretty quickly and without too much stored energy because they're thin and there's small membranes, but then they're cooked.
There's a long way to go on soft robotics.
Yes, there's lots to do.
Do you have any thoughts you'd like to leave us with?
So the thing I'd like to leave with is the strength that comes from adding new kinds of materials together. I experienced that when putting fabrics and textiles with more electronic or mechanical devices, but I see it happening in the MEMS realm and in the soft robotics realm. And some of that doesn't really come from materials or chemistry itself, but just the abilities we have now to do high-speed assembly in machinery. So if you're more of a mechanical background and you're feeling like you're left out, we need your contributions for automation.
Our guest has been Cindy Harnett, Professor of Electrical and Computer Engineering at the University of Louisville.
Thank you, Cindy.
You got it.
Thank you to Christopher for producing and co-hosting. Thank you to Ellie for suggesting Cindy as a guest. Thank you to our Patreon listener support group. Thank you to our patient
support group. It is a support group.
It is. It has been this week. Thank you to our Patreon listener Slack group for their questions, and thank you for listening. You can always contact us at show@embedded.fm or hit the contact link on Embedded FM. And now a quote to leave you with from astronaut Mae Jemison. Don't let anyone rob you of your imagination, your creativity, or your curiosity. It's your place in the world. It's your life. Go on and do all you can with it and make the life you want to live.